Jai Hind to all my dear students. Myself Dr. Neelesh Kumar Gupta. I am working as a professor in EC department at Ajay Kumar Garg Engineering College. So today's my lecture title is what? Optimum and matched filters. This title I have taken your unit number 4 of digital communication. That's AQ2 code is KEC 601. So optimum and matched filter. So I will tell you in this lecture about the optimum filter, then their modification in optimum filter in terms of match filter and their derivations, their expression. Because I am saying optimum filter, I am saying match filter, but what is the meaning of this? How you can prove that it will be optimum filter? Why I am calling optimum and why I am calling match filter? So any mathematical expression from or any proof, you can say that it will be optimum or match filter. That I will tell you in this lecture. So this I have taken from unit number 4. So unit number 4 generally concentrate on optimum threshold detection. So unit number 4 in digital communication of your AK2 syllabus of KEC 601. So digital receiver means what? It means you have to detect the proper and exact signal that you transmitted from the transmitter. If you transmitted 10111 from the transmitter, so at the receiver you can extract what? It must be 1011 exactly. So receiver, so here you have to detect your signal properly, correctly. It means with minimum probability of error and maximum signal to noise ratio. This is the two conditions are, and you can check the performance of digital communication by this. And this performance you can check at the digital receiver side only, because it is output side. If you are receiving, if you are getting, if you are extracting correct and proper signal, proper data that you transmitted from the transmitter, it means the performance of the system is good. That you can check generally from the probability of error and signal to noise. So optimum threshold detection. So detection, whenever you you did the detection at the digital receiver side, so optimum means the best possible result. So generally this term we are using technically, what? Optimum or optimal. Optimal means what? You are trying to get best possible results with minimum probability of error. कम से कम एरर के साथ अच्छे से अच्छा रिजल्ट निकालना, बेस्ट पॉसिबल रिजल्ट इन कंडीशंस. ओके, सो under the optimum threshold detection we will see optimum and match filter concept. Okay, and their derivation, and from the derivation we will see that it will be optimum or match filter. Then BER or probability of error analysis of our various digital modulation technique and your match filter, B and BSK, BFSK, BPSK, M-array, PSK and so on. Then introduction of spread spectrum communication like DSSS and FSS. So these are the main contents of your unit number 4. That's title is digital receiver. Okay, but I will concentrate in this lecture only on what? This, the concept of optimum and matched filters. So digital receiver means what? What I say, that receive signal here, you have to demodulate your signal by using signal demodulator, then detection by the comparing the signal, your incoming signal and their threshold value. Okay, so detection will be there, and finally you will get the output signal after the decision. Okay, because always in digital communication you have to use a comparator at the receiver output side. Why? Because you have to decide whether 1 is coming or 0 is coming. So you have to compare always your incoming signal with any threshold value. Then you can decide whether 1 is coming or 0 is coming. because you have to extract your digital data, binary data that you transmitted from the transmitter. Okay. So now requirement of detection technique in digital receiver. So it must have minimum probability of error, obviously, maximum possible amplitude and maximal what? Signal to noise ratio. Now there are several detection techniques, okay, that's using here, like integrate and dump receiver. This is very basic and easy technique, but this is rarely used. Then you are very important, that is optimum filter and match filter techniques, detection techniques, then correlator or coherent receiver technique. So these techniques that you can use for optimum threshold detection for digital receivers. Now optimum filter. So optimum filter, what is optimum filter? An optimum filter, such a filter used for acquiring a best estimate of desired signal from noisy measurement, because we know our channel is noisy, some noise always must be there, होता ही है, आप कुछ भी कर लो. It is different from classical filter like high pass, low pass, band pass and so on. Optimum filters are optimum. Optimum means what? Optimum means to get the best possible results in your given particular conditions. So optimum filters are optimum because they are what? Designed based on the optimization theory. Optimization theory means to get the best possible result. How? To minimize the mean square error, MSE, or we can say probability of error, or we can say bit error rate between a proceed signal and desired signal, or equivalently provide the best estimation of desired signal from measured noisy signal. So MSE minimize करना and signal to noise ratio को maximize करना, so that you can get the optimum results and you will be able to design optimum filter in that condition. So what is the goal? What is the objective? To find the probability of error. At first you have to determine what is the probability of error, bit error rate, and to find the signal to noise ratio. Generally also I will tell you the expression for getting these values, probability of error and signal to noise ratio in case of optimum filter. Now fundamental of optimum. At first we will see fundamental of this. Let receive signal be in binary format, assuming if we assume polar NRZ format. So polar means polarity plus minus. So if I am taking binary 1, so x1 t is equal to plus a. For binary 0, x2 t is equal to minus a. Okay. And some noise, generally Gaussian noise will be there added into the your x of t. Now from this figure it is that will be clear what, in the optimum filter this input is coming in terms of x1 t or x2 t, for binary 1 or for binary 0, and this xt, in this xt n of t is always additive. If the signal is coming, so noise also will come. Okay. So it will go to optimum filter. Now y of t I am getting up to optimum filter, then it will be sampled or compared at t instant, and finally we will get the y of t. So this y of t is equal to what? X O1 t, or you can say x O1 t plus nt. ये कब बोलेंगे? when we will say this xo1 t plus nt due to the x1 t. If binary 1 we are considering, if binary 2 we are considering, then it will be xo2 t plus nt. Okay, and then decision will be taken. Now xo1 t plus nt, so it means this is the output signal we are getting finally in case of optimum filter. So it is corresponding to x1t signal, x1t input signal. Okay, so it is close to x1t, so we will decide it will be x1t. It is for binary 1. Similarly, if I am getting xot t plus nt, it is close to or approximate to x to t. So, I am considering it will be x2 of t. It means for binary 0. If noise is present, this is our consideration, our assumption ki x01 t plus nt if I am getting. So, I am approximating here what ki x1 due to the x1 t I am getting the output. Similarly, otherwise x2 t I am getting the output corresponding to x2 t plus nt. But if noise is present, it means error will be there. Okay. So, x1 t is selected, yt is closer to x01 t than x02. Okay. And x2 t is selected, y of t is closer to x2 t than x01 t. So, if it is greater, so I am considering x1 t. If it is greater, so I am considering x2 t. Obviously. So, its threshold value, how you decide the threshold value? Threshold value will be the average of these values, x01 t plus x02 t upon 2. So, this will be our threshold value. On the basis of these threshold value, you can decide whether 1 is coming or 0 is coming. Next, so if noise, we know noise will be there. Okay. So, when error will be there? Error कब होगी भाई? कब error होगी? Error जब होगी whenever we are transmitting x2 t, but here at the output x01 t is greater than x02 t. So, as per this, what? If x01 t is greater than x02 t, okay, if nt is positive and larger in magnitude compared to x threshold minus x02, then in this situation what? Incorrect decision will be taken. We are transmitting S2T, but here as per our assumption, we are considering that we are getting the signal corresponding to x1t. So, it is the wrong assumption. It means we are getting incorrect signal, incorrect decision. So, error will be there. If I am transmitting x1t, but I am here what? Detecting the S2t corresponding S22t. So, error will be there. बिकॉज मैंने आपको क्या बताया कि वही सिग्नल जो ट्रांसमिट किया था वही हमें रिसीवर में मिलना चाहिए, यदि नहीं मिल रहा है मतलब एरर है. तो नॉइस एरर इन टर्म्स ऑफ नॉइस, सो इट विल बी व्हाट वी कैन राइट x threshold minus x02. So if you solve, then it will be noise, or in terms of error, in terms of this x01 t minus x02 upon 2. So error will be there whenever you are not getting correct signal, or your assumption, your determination, your detection will be incorrect. Now the probability of noise, so it will be greater than or equal to x threshold minus x02, then it will be x threshold minus x02. Abhi what I calculate this x01 t minus x02 t upon 2. So I am writing this here. Therefore, probability density function of this, because noise is Gaussian noise. Which noise? Gaussian. So, what I told you in unit number 1 and unit number 2, so in case of Gaussian noise, its Gaussian distribution or its probability density function, we can define f of fx n of t is equal to 1 upon sigma root of 2 pi e to the power minus n square t upon 2 sigma square. This is noise square. Okay. So n of t is what? Random process. Sigma is the standard deviation, and generally it has using zero mean and unity variance. That we know. So I am putting here the formula of PDF of what? Gaussian distribution, and putting the value here. Now P is equal to PR n of t. That's I am writing here this similarly. Now if I have to calculate P, so I have to integrate from x01 t minus x02 upon 2 to infinity. What? This PDF into dnt. I am putting the value of that PDF from the last equation into d of nt. Now integrate this. So how I integrate? I am using here substitution method. So I am putting here what? N square t upon 2 sigma square is equal to y square, or y is equal to n of t upon root 2 sigma. Now dy is equal to dnt upon root 2 sigma, or dnt is equal to root 2 sigma into y. Now, if I am putting the value of this is equal to y square, this y is equal to this. So, if I am substituting these value here, so limit will be changed accordingly. So, also limit n of t, whenever n of t get infinity, so y tends to also infinity, but whenever n of t xo1 t minus xo t upon 2, then y tends to this one. So, again p is equal to, we are putting these values and these limits, then your expression will be in this term. Further you solve this one, so 1 upon root 2 pi, root pi integration, the limit from this e to the power minus y square into d y. Now again we have to check here, we have to put here, so let we know 2 upon root of pi integration x to infinity e to the power minus ka y square into dy is equal to what? Error complementary function. This is the formula of complementary error function. So we have to put here, okay, this one in terms of, so this is our final probability of error in optimum filter, that is half of error function, complementary function of xo1 t minus xo2 t upon 2 root 2 sigma. Here you can see if xo1 t minus xo2, it means difference between these output signal, okay. If it increases, then error function value will be decreased, so probability of error also would decrease. So this is the expression of optimum filter, okay, optimum filter probability of error, and you can easily understand how you can get the probability of error in case of optimum filter. Next, after this expression of probability of error in optimum filter, you can also derive the expression for its signal to noise ratio S upon n, okay. Generally S upon n, generally gamma square, by the gamma square we can assume as signal to noise ratio in this. So also you can derive the expression for this gamma square, that is the signal to noise ratio in terms of square term, and also we can derive the its expression for transfer function h of f, okay, or impulse response also h of t. So on the basis of these expression that the base is same, you have to put the value there and you can get the formulas for SNR and what? Transfer function and impulse response. Now introduction to mesh filter. So mesh filter is the modification of optimum filter. If you modify further optimum filter, then you will get the mesh filter. So mesh filter is also type of optimum linear filter for maximizing the signal to noise ratio in presence of additive, stochastic or random noise. Mesh filter are commonly used in radar. Radar means radio detection and ranging, okay, in which a known signal is sent out and reflected signal is examined for common elements of outgoing signal. A very important problem in signal processing is the determining how two signals compare with each other. It's very important in digital receiver. Always you have to determine, you have to estimate about the ones or zero after the comparing the signal. How you compare? You have to compare your incoming signal and your reference signal. Okay. So to give an example, you can program. If we take an example, we can take the program most cell phones to obey the voice command. How does it do? How it recognize that voice is coming? Okay, how it recognize the voice? Your cell phone. The cell phone compares the signal from the microphone to a dictionary of possible phonics and decide which one is the closest one. So also that compare your signal from its standard or set or reference data signal, then decide, okay, So this is the example we can understand about the match filter. It means to synchronize matching means what? You have to synchronize, you have to compare the two signals. Then you have to decide, you can decide. Now in match filter, if we talk about the SNR means signal to noise ratio. Okay. So SIT, it is input signal plus NIT. It will go to match filter of having the impulse response of H of t. Then it will be sample at t stand y of t is equal to SOT plus NOT. So we know here what? SOT is equal to what? Because this is the discrete time signal. This is your X of n, that is your Y of n. So Y of n is equal to what? Output is equal to what? This input and impulse response convolution. So SOT is equal to SIT convolution of HT. If we take its frequency domain, so SOF is equal to SIF into HF. Now if we want to take its time domain, SOT is equal to, so it will be minus plus infinity SOF into e to the power j2 pi ft into df. Now SOT is equal to minus plus infinity SOF is equal to what? This. You can put the value of here SOF. So SIF into HF into e to the power this. Okay. So this is SOT. It means your output signal in this match filter. So if I want to take its square, so SO square t is equal to integration modulation fee SIF into HF into this ka its whole square. Because what I told you, signal to noise ratio always you have to show in square terms, gamma square, signal square upon noise square. Now SNR, what I said, SO square t upon sigma square. So if you put the value here, okay, I know sigma square value that you can get the in case of optimum filter H square F into GNF. GNF means what? It is the what? Power spectral density of noise. Okay. So this now using the Schwarz inequality. So you have to make this formula as per the Schwarz inequality. If you transform this as per the Schwarz inequality, so you will get this term as per the Schwarz in this way. Now we know the noise is wide Gaussian noise, so GNF, that is the power spectral density of noise, it is equal to N0 by 2. So now S02 square t upon sigma square is less than or equal to integration minus plus SIF whole square or DF upon N0 by 2. So this is our signal to noise ratio. It will be this one. Okay. So in this way we can derive the expression for signal to noise ratio for match filter. Okay. Similarly, we can also go in terms of energy of the signal. Okay. So if we know energy of the signal, what it is in minus plus infinity SIT square into dt, it means SIF whole square into df. So in terms of signal energy, it will be in this way. Okay. So also you can give the signal to noise ratio in terms of energy of the signal, and it will be equal to 2 of E, 2E upon what? N0. Now also we can get the transfer function of the match filter. So we know Y of f is equal to k into x conjugate f. We know this will be HF into e to the power j 2 pi ft is equal to k into SI conjugate f. Now also transfer function is equal to, it will be in divide in another term. So k SI conjugate f into e to the power plus जैसे क्या हो जाएगा minus j 2 pi ft. So this will be the transfer function of match filter. So these derivations generally will be asked in examination. So carefully you have to understand here. Now impulse response, it means this is the transfer function. If we want to take its time domain, so it will be impulse response. So this is the impulse response h of t. that will be minus plus infinity h of f into e to the power j 2 pi f t df. So h of t is equal to integration minus plus infinity. So I am putting the value of h of f from last PPT here. Okay. So it will be what? K, you can take the outside of the integration, then SIF conjugate e to the power minus j 2 pi f t capital T minus t into df. Now for realize any filter, we know it should be real. So h of t simple, its real term and its conjugate term or imaginary term, both are equal. So h of conjugate t is equal to k SIF into e to the power j 2 pi f t minus t into df. It is k SI what? This is what? This is your frequency shifting property or time shifting property. If you understand Fourier transform, by the shifting property, it will be convert into the k into this will be SI capital T minus T equal to ST. So this is the formula, final formula of impulse response of mesh filter. That will be in terms of your input signal, input shifted signal, capital T minus small t. Okay. Now mesh filter is the optimum linear flow maximize signal to noise ratio in presence of additive noise. Okay, that I also told earlier. These are commonly used image processing and improve the SNR for X-ray picture. So generally in communication, whenever you want to maximize your SNR with minimum probability of error, you can use the meshed filter. Okay. Also, we will get the probability of error in mesh filter by this derivation. Okay, by this expression, we know POT is equal to mesh filter. What I have taken SO1T. So P is equal to 1 half error function POT upon sigma 0. Okay. So by this formula, what? Half error function P0 T whole square, sorry, P square, P0 square T upon 8 sigma square T 1 upon 2. So we have to transform this term into this term. Okay. So we find that minimum probability. We have to minimum probability. If we want to achieve minimum probability, so your signal to noise ratio will be maximum. If signal to noise ratio is maximum, then your error will be minimum. Obviously, because these both are inversely in each other. So here PE minimum is half error function, complementary function of 1 upon 8 P0 square T upon sigma square maximum to the power 1 by 2. If I am reducing this, so it will be in terms of what? Energy of the signal. Okay. Similarly, if I am calculating the probability of error in match filter, similarly we can also get the probability of error in ASK, FSK, PSK, QPSK, DPSK, MRA, PSK, MRA, FSK, MRA, and so on. So if I want, I am only just giving the one example, okay, of ASK technique. So probability of error is your P is equal to half error complementary function 1 upon 8 R maximum square 1 up. This is your signal to noise ratio. Okay. So at first we have to calculate R maximum square, signal to noise ratio we have to. So it is the formula for this 2 upon eta 0 to integration 0 to capital T S1 T minus T whole square into dt. So in ASK we know this is on off signal, on off signaling. So 1 or 0, bit 1 or bit 0. So if I am taking S1 T is equal to A cos omega 0 T, so S2 T is equal to 0. So binary 1, for binary 1 your whole signal you are getting, for binary your signal is 0. So P of T is equal to S1 T minus S2 T. So it will be A cos omega 0 T. Now I am putting these values in R maximum square 2 upon eta A square cos square omega 0 T dt. We know cos square omega 0 T is equal to 1 plus cos 2 omega 0 T upon 2. So I am putting here and simply this one and integrate in two terms, okay, and I am getting R maximum square is equal to A square T upon eta, okay. Now probability, if I know what P is equal to half of error function 1 upon 8 R maximum square to the power or square root of this term. So I am putting the value and I am getting this will be our probability of error. Okay. Similarly, probability in terms of Q function and so on we will calculate, or we can easily calculate for another modulation techniques as in ASK. Similarly, the same formula we have to use and easily we can achieve probability of error and so on after calculating the maximum signal to noise ratio for any modulation technique. Now, coherent reception or correlation. So, block diagram coherent receiver. Coherent receiver means correlator, like you can say coherent receiver or we can say correlator receiver. So, the combination of multiplier and integrator is called correlator. So, this is another detection technique. I told in my second PPT of this lecture, one method is also correlation coherent reception method for detection technique. So, in this technique what x of t and t is coming, x of t in terms of x1t or x2t, it means for binary 1 or binary 0. So, at first it will go to multiplier. So, multiplier compare this signal, okay, or multiply this signal and locally generated signal and goes to integrator. Integrator means low pass filter. In the detection side always we have to use integrator because integrator always works as a low pass filter. And it will go v of t, and after the synchronizing and sampling at t is equal to capital T, it will generate the XO1t plus N0t or XOTT plus N0. Okay. So, in this way using the coherent reception or correlator receiver, we can also detect our original signal after the comparing your incoming and threshold signal. Okay. So, these are the detection techniques, okay, at digital receiver that we can prefer at the detection time so that we can decide correct and proper data of binary data that we transmitted actually from the transmitter side. So, thank you very much. Jai Hind. Goodbye.